What's up, everybody? Mr. McCarson here. Just letting you know, so what I ended up doing with this video is I split it into two parts. So the second part you're going to watch now, part two, is all about mixtures. So what we're going to be talking about is different types of mixtures in terms of homogeneous versus heterogeneous. We'll talk about suspensions, solutions, colloids, and emulsions. So go ahead and give this part two a watch and understand that the big topic here is to understand what is a mixture and how is it different than a pure substance, and then what classification system do we have for mixtures in chemistry. All right, enjoy. Have a good one. Bye. Okay, so we've talked about pure substances in terms of pure elements and pure compounds, and we've discussed the difference between compounds and molecules. Now, what we're moving on to are mixtures. Now, mixtures are very different than pure substances, okay? So, a mixture is defined as, let me get my pen here, a blend of two or more kinds of matter, each of which retains its own identity and properties. So I can take copper beads that we used in lab and drop it into a beaker of water, and that's a mixture, right? I put copper and it's touching and it's mixed into and it's physically interacting with the water. Now, when I put them together in that mixture, the copper isn't changing the water, and the water's not changing the copper. They're simply existing mixed together in a defined area or space. Okay, now that does get a little bit more sophisticated than that example. That was a little simplistic, but we have two major types of mixtures. The first is a homogeneous mixture. You could also say homogeneous. That is another acceptable pronunciation. And we think of these not exclusively, but sometimes as solutions. And you're going to hear that word a lot in chemistry. We're going to make a salt solution or a sugar solution, okay, or a solution of copper 2 sulfate, okay. Now, a homogeneous mixture, the prefix homo meaning the same, okay, is something that is uniform in composition. And uniform means the same throughout, right? So when I think about a homogeneous mixture, the classic one, right, is the addition of salt, table salt, sodium chloride to water. Why is that one famous? Because and it's not the only salt mixed into our ocean, but we think about our oceans and salt water in our oceans, right? If you take a tablespoon of salt and you mix it into a glass of water, generally you're going to see that salt do what? It disappears, right? It interacts in a special way with the water molecules, which spread it out uniformly, and it causes it to become a homogeneous mixture. Now, heterogeneous, and hetero meaning different, so a heterogeneous mixture is not uniform in composition. Has anybody ever tried to mix oil and water? Doesn't work well, does it? Okay, so when you mix two things and they are not able to mix in uniform distribution or non-uniform composition, that is a heterogeneous mixture. I kind of think of them like my analogy that I like to use is I think of cookies because I'm a foodie and I got a sweet tooth. So I think of chocolate chip cookies versus sugar cookies. Okay, now keep it simple here. Like you go to Costco, and I love Costco. Okay, once again, you want to do any sponsorships, Costco, look me up in the email link below. But when we go to Costco, I can't help myself but get the box or the that plastic tin of the big chocolate chip cookies from Costco. Now, a heterogeneous mixture I think of as the chocolate chip cookies, and here's what I mean. When you get a chocolate chip cookie and you take one of like the 15 or 20 cookies you get from that little container, okay, when you look at the distribution of chocolate chips and you compare it between two cookies, does every cookie have chocolate chips in the exact same location? Or are they randomized? Are they non-uniform? Hopefully your answer to that is non-uniform. No two chocolate chip cookies have exactly the same distribution of the chocolate chip chunks within the cookie. And that's what makes it kind of fun and unique. Like, and I often look inside, I find the one that's trying to load it with the chocolate chips. Okay, if you know, you know. But that's for me a heterogeneous mixture. And when you get two chocolate chip cookies, you know they're chocolate chip because it's cookie dough and chocolate chips mixed together in deliciousness. But you think of it as heterogeneous because you can bite one side of one cookie and get nothing but cookie dough, and you bite the other side and get a big old glob of chocolate. So the distribution is not uniform. Now, for a homogeneous mixture, I think of sugar cookies or something like a vanilla wafer or, a simple plain cookie. Maybe like, I forget what they're called, but the ones the Girl Scout cookies sell, like they're really good and delicious. And if your siblings sell Girl Scout cookies, let me know when it comes that time of the year because I'm a sucker for those. I'm a sucker for those tagalongs. Now, in a homogeneous mixture, you have uniform composition throughout. So when we think of a sugar cookie, right, the distribution of a sugar cookie, no matter where you take a bite of the sugar cookie, all the components are blended evenly. So if you bite the top of the cookie or the left of the cookie or the right of the cookie, doesn't matter, you should get the same flavor distribution throughout the cookie because it's all of the particles that are mixed together are evenly blended or they're uniformly mixed in the same throughout the composition. Okay? And shout out to Psyduck here, one of my favorites going all the way back to my early Game Boys, which I still have the save files on. Okay, so mixtures, blend of two or more kinds of matter, each which retains its own identity and properties. We have two main types of mixtures, and we're going to explore them in a deeper fashion. Homogeneous mixtures, which are uniform in composition, versus heterogeneous mixtures, which are non-uniform in their composition. Okay, on to the next. All right, so I like this slide. This is an example of homogeneous mixtures. So this is a nice visual representation. So for homogeneous mixtures, we have things like coffee, okay, wine, air, brass, steel, natural gas, vinegar, and blood. So the big thing here is they're uniform in composition. Are there particles mixed together of different substances in there? Yes. So for example, steel is going to be iron with a small amount of carbon atoms. But the idea is when you make the steel really high quality, the carbon atoms are spread out and distributed in a very even and uniform pattern, and that makes the steel very durable and strong. Same thing when we talk about air. Air is it's mainly 78% nitrogen, 21% oxygen, but within that mixture, the uh, the composition is pretty uniform. The oxygen is distributed at a pretty even rate throughout the nitrogen, okay, along with the other particles there. So these are some examples of homogeneous mixtures that you might encounter, and you want to be able to kind of think about and rationalize why as you go through the worksheets and quizzes and test on the material. All right, here is a competing example. So here we have heterogeneous mixtures. And the big thing, like if you think about it like with atoms, in heterogeneous mixtures, the atoms are randomized. They're not in a uniform pattern. Their pattern is erratic, or, like you've got splotches of different atoms here or there. So an example of a heterogeneous mixture is a salad, right? So like in a salad, you've got different amounts of carrots and cucumber slices and little tomatoes, those cherry tomatoes, and they're all kind of randomized. There's not like for every lettuce there's two carrots and one tomato. It's distributed randomly. Another example of heterogeneous mixture, like ice cubes in a drink. The ice cubes don't line up perfectly. They bounce off each other. They generally float to the top. There's no ice cubes at the bottom because of the density of ice versus liquid water or liquid substances. Smog is a heterogeneous mixture, and smog is kind of a big problem in California right now. Um, and we always kind of want to do our thing to try and make sure we keep that air clean. But smog has very heavy particles, and the problem is their density compared to the general atmosphere are so heavy that they hang closer to the surface of the Earth, where we walk around and breathe and play sports inside of, and that can be problematic for our health. You got to take care of yourself out there. So these are just some examples of heterogeneous mixtures. All right, so we're getting close to the end to this first part of part one of properties of matter. And what we're going to talk about now is different types of mixtures. Now, when we talk about these types of mixtures, these have special names and properties and classification features. But ultimately, we will think of each of these as homogeneous or heterogeneous. So in the first one, we have what's known as a suspension. And these are where solid particles float in a liquid or gas. Okay, and these particles will settle when the mixture is allowed to rest. Now, suspensions are classified as heterogeneous. The most famous suspension that most teachers use when they discuss this with students for the first time is we think about suspensions as things like Italian salad dressing. In Italian salad dressing, you've got the primary background, which is usually like water and vinegar, but then you have oil, and then you have the herbs and seeds. And what happens is the vinegar and oil levels don't really like to mix, so they settle into different layers, and then the chunky herbs and particles are the densest, and they go all the way to the bottom. And then what happens is if you take that salad dressing, what are you supposed to do before you put the salad dressing onto your salad? You shake it up. Okay, you shake up that salad, and what it will do is the bigger chunks of like herbs and seeds, all the good stuff, will, and the droplets of oil, you'll see the oil start to float around and become suspended in the bottle of salad dressing, and then you pour it on and you get your salad, you get your greens. Um, the problem is, as soon as you put it on the table and you start to give it time, gravity will separate those layers out by density. So we classify suspensions as heterogeneous. Now, compare that and contrast that with solutions, which are homogeneous mixtures in which one substance, the solute, dissolves perfectly into another, the solvent. Okay? Now, the solvent is what does the dissolving. The solute is what gets dissolved. And we have an entire unit later in the second semester concerning solutions and the mathematical chemistry behind them. Okay? Solutions are very, very organized in terms of we know how much solvent and how much solute interact together for things, for example, like water and salt. We call that solubility, the ability of a solute to fully dissolve in a solvent is something that we're going to discuss in great detail later on. And we say, and this is a big thing, all solutions are homogeneous. All solutions are homogeneous. Okay, and the classic solution is salt water. Um, but other things can, and water is known as a universal solvent, and we'll discuss why when we get into chemical bonding and polarity. But water is one of the greatest substances, if not the greatest, in the universe at dissolving a wide variety of other compounds, molecules, and elements. So solutions always homogeneous. Now, a little bit more weird and difficult, but they're also generally considered homogeneous, are colloids. And colloids are where you get tiny unmixable droplets that float in a different substance. Now, these particles, the big difference between a colloid and a suspension is in a colloid, the particles do not settle to the bottom of the mixture. Okay? Now, colloids are considered homogeneous because they're generally evenly distributed. So even though they float the same in the top, middle, and bottom. Now, I think of my, like, kind of my greatest colloid, the one I like the most, because I grew up eating a lot of cereal. And my mom would always get mad because she'd buy a box of Cinnamon Toast Crunch, and my brothers and I would dust it in like a day. It was, yeah, she was always like, there was never enough cereal that she could get at the store for us that would last. Cereal didn't last a week in my house with three boys growing up. Now, milk is a colloid. Okay, that big old side talk for the idea of milk being a colloid. No, now in milk, the primary solvent is still water. So like water's in the background of milk, but what you get is little tiny droplets of like sugar and fat that float, and that's what makes it so delicious. That float around, but they're very tiny. Like they're not visible to the eye. So for us, we can't actually see the particles in milk with our naked eye. There is a technique to tell colloids from solutions, and we'll talk about it later. It's a special lab technique. But colloids or substances like milk are considered homogeneous. And the big thing is the particles stay suspended, they float, they do not settle into layers based on density. That's what makes it homogeneous, while suspensions are heterogeneous. Now, there is a special type of colloid called an emulsion, which are where like liquid colloid drop it, or a liquid colloid in which droplets of an unmixable liquid float in another. And emulsions, like the best way I think of it is emulsions are things like lotion. So like in lotion, you have multiple liquids mixed together and they're not actually like interacting in a way where they're dissolving in one another, but like one type of chemical will float in another. And that's how you get things like hand creams or Jergens lotion, okay, or any of those other types of lotions out there, right? And being a colloid, they're generally considered homogeneous, right? Unless you get those lotions that have like the little grains in there to like exfoliate. That might be pushing a little bit, but that could be some other kind of classification. But in general, just like a hand lotion is a good example of an emulsion. All right, so I really like this diagram. I think it gives you a good visual and explanation of the difference between solution versus colloid versus suspension. So remember, all liquid mixtures contain particles. The size of the particles determines whether the liquid is a solution, colloid, or suspension. So like in suspensions, the particle sizes are much larger. So particles are greater than 10 to the minus fifth centimeters, okay? So they're generally large enough to see with a human eye, okay? In a colloid solution, they're actually particle sizes are smaller. They're between 10 to the fifth negative fifth centimeters and 10 to the negative seventh centimeters. And they're, once again, for the human eye, unless you're using special instruments, you're generally not going to see them. Like you don't see the particles floating around in milk. To us, milk looks like a creamy white substance, the same all the way throughout. Now, in a true solution, the particle sizes are so small they actually disappear to the human eye, right? In most true solutions, like if you take table salt and mix it into water, so long as you don't go above the solubility amount, that table salt, when you stir, will disappear, okay? But particle sizes are less than 10 to the minus 7 centimeters. So in a solution, they're so small, the water is able to completely surround and actually block them from our view. That's why we can't see them. In a colloidal solution, they're so small that our eyeball can't distinguish between them. And in suspensions, we can actually see many of those particles floating around. Okay, so here's where we're going to talk about that lab technique to distinguish between solutions, colloids, and suspensions, and it's known as the Tindle effect. Okay, so the Tindle effect is where you take a sample of a solution, a colloid, and a suspension. And what you do is you take a nice flashlight, you take a beam of photons, a beam of light, okay, just white light, and what you do is you hold it up to the glass container that contains the substance, the mixture you want to analyze. Now, in a solution, if you hold a beam of light up, you will not see any light go through that water, right? You're not going to see any beam go through that glass of water. It's really bizarre, but it has to do with reflection and or the refraction of the photons through the water molecules that are there. Okay, so the Tyndall effect is the scattering of light by particles in a colloidal suspension. Now, in water, there's no beam of light visible. Why? Because it's a true solution. In a colloid like milk, if you hold a flashlight up, you're going to get a tiny amount of scattering. It will look like a continuous beam. So you're going to get a smooth beam of light through the middle of the milk. Why? Because that light is bouncing off the tiny particles in the milk. They're large enough to reflect the light back into our eyeball, okay? But it will look like a smooth beam. Now, in a suspension, it's going to sparkle. Because the particles in the suspension are very large, it will actually sparkle in a way that's much more of a visually striking impact than in a colloid, okay? So the Tyndall effect, you get a smooth beam in colloids, you get a big sparkly beam with sparkles in a suspension, and in a solution, there is no visible Tyndall effect or Tyndall effect. Okay, very important technique, the Tyndall effect. All right, so here's my last slide for part one, and we'll do part two in another video because this is now getting pretty long. So this is a nice classification of matter concept map. So I really enjoy this one. I think it does a good job of breaking it down. And remember, we start off with matter, And we can break matter into two major pathways when we classify it. So we can have pure substances and we can have mixtures, okay? Now, pure substances, we can think about either a pure element or we can think about compounds. Okay, now in pure element, these are atoms from the periodic table. So when we talk about pure elements, these are all from our periodic table, of which there's 92 naturally occurring pure elements on planet Earth. Compounds are combinations of two or more different elements in a specific ratio, right? So CO2, water, SiO2 is silicon dioxide, that's what's in sand. NaCl, table salt, sugar, C12H22O11, known as sucrose, because there's lots of kinds of sugar. So anyways, for pure substances, we have elements and compounds. Now, for mixtures, we have two major classifications. The first one is homogeneous mixtures, of which we have solutions, and then we have colloids, okay? Now for solutions, these are things like Kool-Aid, tea, air, soda, brass. And for colloids, we have things like paint, milk, fog, foam, and honey, okay? Now, remember, once again, what does homogeneous mean? Uniform composition, or the same composition throughout the mixture, okay? Now, for the second type, we have heterogeneous, which means non-uniform composition or randomization of the mixture throughout the sample. And for heterogeneous, we're talking about suspensions. And examples of suspension are trail mix, which oddly enough, when a bowl is placed in front of Mr. M, no longer contain M&Ms, right? Why do the M&Ms always disappear first out of the trail mix? Water and oil, pavement, or spaghetti sauce. So anything, or chocolate chip cookies. So anything with randomized distribution in the mixture, we classify as heterogeneous. So there's a lot here. Thank you for being patient with me and getting through part one. I'll come back with part two, where we explore intensive versus extensive properties and physical change versus chemical change. Thank you. Have a good day, and I'll see you again on the next video. Bye, everybody.